Hello everyone, welcome to the Coherence and Quantum Entanglement week 12 for this NPTEL course, which is the last week and this is the last class and last time we are meeting for our regular Saturday interaction, basically problem solving and doubt clearing session, which used to be happen every Saturday 5 p.m. to 7 p.m. and this is the last time we are conducting this. And of course there will be another 1 hour summary session that is I will just summarize all the course and give some recommending problems and some discuss about the whole syllabus what we have covered and what are the rules and regulation that you need to follow for your examination purpose. So those things will be discussed in that 1 hour session, but apart from that today is the last week 12 problem solving and doubt clearing session for this coherence and quantum entanglement. This was a great journey for past 4 months, and I hope everybody of you have enjoyed this course and eventually you came to know all of the topics that we promised to you to tell. So based on that, you know what is the syllabus you have this if you go to the, so as before going to that I will just want to say that I just want to formally introduce the course for last time again in today. So first thing is that as I used to say all of the necessary things that where we will get all of the necessary documents, those things let me mention once more, and that is for the last time, that is today that is for the last time today. And the thing is that if you want to access all of this video session recording session of this problem solving and doubt clearing sessions, then you can find those in my YouTube channel, which is this, and this is the channel link. If you search it Nilaksh Chanapati, then you will be able to get in the YouTube, and this is the channel link that I am providing in the chat box. And this is the Google Drive folder where you can find all of the materials that I have used in this discussion session. I have the class notes, the extra materials, as well as these slides. So this is the Google Drive folder, and where you will get these slides also. And now this is the Google document folder, this is the this is the Excel sheet which is already shared with you via NPTEL portal through through SWAYAM portal by NPTEL. That is also there, but I am again sharing the link of this Excel sheet also. You can access all of them, and if you want to know that where you will get this, then you can of course go to the Coherence and Quantum Entanglement course for NPTEL course, and if you log in there then you will be able to you will be able to access and find all of the necessary documents like assignments, your quizzes, your solutions, lecture notes, and these kind of Google spreadsheet links also, where you can see that here it is written as problem solving session 2024. If you click over there, then you will be able to get to see a link where this if you click this, then it will redirect you to this Excel sheet where you will be able to access all of the necessary links of the YouTube channels as well as the Drive folder. And of course by the time you all are aware about all of the things that you will get to know about any announcement via your mail and as well as in your course page. And this is the this is a Q&A page that I used to mention all of the time, that if any one of you any one of you that if you have this question, if you have any question, then please go there and answer and question and ask the question. We'll answer the questions in the problem solving and discussion session, or we of course will reply to you also here. And you can see many of the people have asked many questions and we have answered. And until unless the examination date is there, or this is the until unless tomorrow we will be able to, we will give all of the answers of the questions. After that we will stop this with the ending of this course we will not be able to access that Q&A portal, that will be refreshed again. So take your last opportunity to discuss with us. You can also mail me. I always share my mail ID, and this is the mail ID of me, where you can where you can get in touch with me. And there are several people who used to mail and ask for the books and all of the stuff. I used to share with them by mail. And if you okay, so this is the, and of course there is that, and there is another medium through which you can contact me, is that if you click the video, go to the video, then you will find there is a comment section corresponding to each and every video. There you will be able to comment or ask question. I'll of course answer the questions. So those are the necessary things that I used to tell every time, and I also again mentioned today. So now formally start today's class, where we will discuss about quantum cryptography, quantum teleportation, and solve many questions. So this is the first question for you, which we will solve today. We'll start today with some problem solving. Let me show you what is today's plan. We will first start with some problem. This is the problem 1, and then we will discuss about quantum cryptography. We'll solve problem, again we'll go to the quantum teleportation, we'll solve problem, and we will end up today's session. So this is today's plan. So mainly our focus will be problem solving, quantum cryptography, and quantum teleportation. This is the plan for today's discussion session. Okay. Meanwhile, I would just like to mention to you that as the examination is approaching, you need to be very quick with the problem solving things, and you should be able to solve the problems, as well as you should do the practicing for all of the questions that is provided to you via quizzes, assignments, and these kind of problem solving and interaction sessions. So I hope all of you are already started your practicing, and it will help you. And anything and everything, if you need from me any discussion, any questions, please write the questions in the Q&A portal, or write to me via mail, or YouTube comment section, or whatever, because this is a last opportunity so to contact with us, as well as this is going to end. So we want it to be a very successful course, and I hope you guys have enjoyed and enjoying, and again some point of time maybe this course will again run, and then again many people will register for it and work for it. So this is a very highly recommended and hot topic nowadays, coherence and quantum entanglement, and this will of course help you for in many cases. I am not going into the that perspective, but rather now start solving our first question. So this is a problem 1. I'll give you 2 minutes time. You just go through this problem, and then I will start discussing of this question. I will thoroughly solve the problem as I used to do every time. Okay, let's see what is the question here. The question is saying that consider a two particle state psi1 equal to a h h plus b v v, where a and b are real numbers and where a squared plus b squared equal to 1. Consider another two particle state psi2 equal to p h v plus q v h, where p and q are real numbers and where p square plus q square equal to 1. Write down the density matrix rho 1 corresponding to state psi 1, then calculate the concurrence of psi 1. Now consider a two particle state that is an incoherent mixture of state psi 1 and psi 2 with equal proportion. Write down the density matrix rho corresponding to this state and calculate the concurrence of rho. This is very nice, very elegant, very simple question. So now we will solve it, and I hope you have already started and you guys know what is actually what is telling here actually. But all right, so yes, this is a question, and now it is saying, first let me write this psi 1. This is a problem 1. Psi 1, I hope everybody of you can see my writing pad. A h h plus b v v, where a and b are real numbers, and now I need to find out the density matrix. Very simple. That is equal to rho 1 equal to psi 1 psi 1. I hope you guys can understand what is the meaning of what is the meaning of HH and VV state. Of course, I think so. H is a H is a just H is 1 0, and then HH is a 2 photon 2 like H is like 2 cross 2. I mean, I hope uh, like um, can you understand that if I do the psi 1 like this to get the density matrix, what will be the row cross column? Okay, so maybe I will not tell, let me do it, then you will be able to understand. This will be 4 cross 4, right? Whoever has answered 4 cross 4, they are all right. Let me do right step by step. Now I can understand, you guys can understand that it is 4 cross 4, and I can write in matrix form like so. This is the density matrix. A. This is the first question. Now the second question, it is asking calculate the concurrence of row 1. Okay, so we know what is concurrence, we know how to calculate the concurrence, and we'll just follow the similar steps to calculate that thing. So the concurrence of these 2 qubit density matrix can be calculated like in these steps whatever I will follow. And this kind of question is not given there in your assignment or quizzes. That's why I am doing this in the very first or very beginning of this class, such that you guys can go through this and practice this and remember this, because this is very important for your examination. Now take the 2 qubit density matrix row and construct a density matrix row bar using the spin flip operation. The theoretical explanation and what is concurrence and why we are doing spin flip operation of the density matrix, that is already described in the lectures and in previous discussion session. So this is the tensor product. Sigma y's are Pauli spin matrices, y matrices, and rho star is the complex conjugate of that of the rho. Rho is where and sigma y cross sigma y, where sigma y is the 0 minus I 0 is a Pauli y matrix. Now construct a new matrix rho bar. And find, I am writing steps. This is step 1. For this kind of problem, what you need to do, that I am mentioning. This is step 1. This is step 2. You can get any kind of density matrix, any kind of state through which you need to construct the density matrix, and then the corresponding row bar and the row bar. And once you get once you get the row bar, then step 3 is find its eigenvalues and arrange them in the find its eigenvalues and arrange them in descending order. Lambda 1, lambda 2, lambda 3, lambda 4. The concurrence, then step 4 is you need to calculate the concurrence, that is 0 maximum of 0 root over of lambda 1 minus lambda 2 minus lambda 3 minus lambda 4. Please follow these steps for any this kind of problems. Okay, so for our case, which is this is the row 1, we will found the row 1 bar, and I am directly writing the answer what it will be, because I have already calculated. Please do it by yourself. This is nothing but the matrix multiplication and calculation and tensor product, so you will be able to do. So once this matrix is constructed for our case, now we can calculate the eigenvalues, and the eigenvalues for this will be 4a square b square 0 0 0, and this is in descending order. That means this is the highest one, these are the lowest one. Therefore the concurrence will be 2ab. I am just following. This is the step 1, step 2, step 3, step 4, and for us this is the step 2, this is the step 3, this is the step 4, and I am finally able to calculate the concurrence. In between matrix multiplications I am not doing, those are very familiar to all of you, so you can do. So this is the part B, which is asking for calculating the concurrence. Now let me go to the part C. It is asking now consider a two particle state that is in incoherent mixture of state psi 1 and psi 2 with equal proportion. Write down the density matrix rho corresponding to this state. So this is the part C. And the density matrix in this case rho is equal to, as it is mentioned, for equal proportion 1 by 2 psi 1 plus 1 by 2 psi 2 equal to half. The matrix will be, if you calculate, where psi 1 and psi 2 is given to you. Psi 1 is equal to AHH plus BVP and psi 2 equal to PHV plus QVH. Now calculating this rho. This is the density matrix. Now, in order to calculate the concurrence, which is given in the part 4, that calculate the concurrence rho, you need to follow the same procedure. I will directly write all of the steps I have already calculated, such that you do the in between steps by yourself, and as well I save some time to do other problems and other things. That's why. So first you need to calculate rho bar, and I am directly writing the rho bar for this case, which is half a square b square 0 0 a cube b 0 p square p cube q 0 0 p cube p square 0 a b cube 0 0 a square b square. Okay. Now if you calculate the eigenvalues, then the eigenvalues are a square b square p square q square 0 0, and the concurrence will be maximum of what is root over of either AB minus PQ or PQ minus AB. So this will be the answer. So this was the part. This was this problem. Okay. Now I will discuss about quantum cryptography. I will start about the quantum cryptography, but meanwhile you just look at the problem once again and try to understand what I have done and what are the process one by one, step by step, that I have gone through. Those are nothing but the matrix multiplications. You just understand, and I will start the quantum cryptography now. I will describe about it. Okay, so cryptography is the art of combining a message with some additional information called the key, such that the combined messages becomes unintelligible to every person except to the intended receiver who has the key. So cryptography is used for secure communication. A key is shared between the sender and receiver, which is you can say as Alice and Bob. A is the sender, Alice is the sender, and Bob is the receiver. The sender encodes a message with the key, and the receiver decodes the message with the same key. And the main aim of this cryptography is the secure distribution of the key between sender and receiver, such that no eavesdropper comes into the scenario and one can hack that. So in the quantum domain, the key distribution is achieved through the use of quantum principles and is therefore called quantum key distribution. There are two generic protocols for doing quantum cryptography. One is called BB84 protocol, which requires single photons and which utilizes the principle of superpositions. The other protocol is called the Eckert protocol. It requires pair of photons that are entangled in a two-dimensional polarization basis. In the BB84 protocol, the sender, that is Alice, prepares a state in a randomly chosen basis and sends it to the receiver. Bob then measures the state sent by Alice in a separate randomly chosen basis. In Eckert protocol, Alice and Bob each receives one particle of the entangled pair. Alice then chooses a basis randomly and measures the state of her particle. After Alice's measurement, Bob also chooses a basis randomly and measures the state of his particle. The two proposed protocols are very similar in the sense that Alice is measuring a state in the Eckert protocol is analogous to her preparing a state in the BB84 protocol. With this analogy in mind, we will discuss the BB84 protocol only. So security in classical key distribution depends on the security of the communication channel. However, quantum key distribution is intrinsically secure because of the laws of quantum mechanics. If quantum key distribution succeeds, it is perfectly secure. So you can understand. Now we can ask one question: that what are the laws of quantum mechanics that makes quantum cryptography perfectly secure? One is measurement in an incompatible basis changes the quantum state. For example, if a horizontally polarized photon is measured in the H or V basis, the measurement will find the unit probability the state of the photon to be horizontally polarized, and after the measurement state of the photon will remain horizontally polarized. On the other hand, if the photon is measured in the plus 45 minus 45 basis, half the time the measurement will find the photon to be in plus 45 polarized, and other half of the time the measurement will find the photon to be minus 45. And second one is a no cloning theorem. This theorem states that the arbitrary state of a photon cannot be cloned. How we can prove the no cloning theorem? Let me show you. So the proof is that suppose there is a unit operator U cap that can clone a photon in the HV basis, that is U H gives me HH and U V gives me VV. The same inhibitory operator when applied to plus 45 degree polarized photon, then it becomes U H plus V is H plus VV, which is not equal to H plus V, H plus V, which is supposed to be. Thus, we see that an arbitrary quantum state cannot be cloned. So, even if the photon sent by Alice is captured by some eavesdropper, the eavesdropper cannot always make a clone of the photon and send the original photon to Bob. As a result, any act of eavesdropping will result in an error in the state received by Bob, and this will allow Alice and Bob to become aware about eavesdropping. This way, quantum key distribution is perfectly secure. Now, as you can see here in this slide, that as you can see in this slide that this way of quantum key distribution can be done in 5 steps. First is written as distribution of a raw key. The first step is to generate a key called the raw key, and then in the BB84 protocol, Alice prepares the state in a randomly chosen basis and sends the state to Bob, who then measures it in another randomly chosen basis. The sequence of states prepared by Alice and sequence of states measured by Bob constitute the raw key. The raw key, of course, contains error, and there is also possibility that a potential eavesdropper may have some information on the key. Now, second step is to do the basis reconciliation. The next step of quantum cryptography is called this. In this step, both Alice and Bob publicly announce their basis for each set of prepared and measured state, and after that keep only those measurement results for which both of them happen to use the same basis. The key obtained after the basis reconciliation is called the shifted key. In the absence of an eavesdropper, the shifted key contains no error because for each set both Alice and Bob use the same basis, and so their measurement values are the same. However, the presence of an eavesdropper in the system introduces error in the shifted key, because a measurement act by an eavesdropper alters the state sent out by Alice and thus causes an error in Bob's measurement even when Bob is measuring in the same basis used by Alice to prepare the state. This fact is because of the no cloning theorem of quantum mechanics, which indicates that an arbitrary quantum states cannot be copied. And in fact, it is this feature of quantum mechanics that makes quantum cryptography 100% secure. At least I am talking like in principle case. Now the third step is error estimation, the goal of which is to estimate the error in the shifted key. In this step, both Alice and Bob select a random set of measurement results and then compare them publicly. If they find the error to be below the maximum allowed value, they proceed to the step 4, I mean the next step, and 5, and like if it is not so, like if it is the error is below the maximum allowed value, then they simply abandon the protocol and start over again. Now, if the error obtained in the third step is below the allowed limit, then the fourth step in quantum cryptography is the error correction. In this step, Alice and Bob use different techniques to minimize the error in the shifted key. The length of the key obtained after error correction is invariably smaller than that of the shifted key. Okay, although the key obtained after error correction is nearly error free, there is still a possibility that an eavesdropper or Eve has some information about the remaining key shared by Alice and Bob. In fact, most error correcting codes end up increasing Eve's information on the remaining key. Now, last but not the least, that is the fifth and final step in quantum cryptography is the privacy amplification, and the aim of which is to minimize Eve's information on the remaining key. This fourth and fifth states are common to every cryptographic protocol, irrespective of whether it is quantum cryptography or the present day classical cryptography. Therefore, the main goal of quantum cryptography is to generate a shifted key with an error that is below the maximum allowed value. The hallmark of quantum cryptography is that once it is successfully completed, one can be absolutely sure that no eavesdropper has any information on the shared key. Okay. So we discussed about these five steps. Now we will learn about the quantum cryptography, BB84 or ECART protocols. With this slide. Now you can see the BB84 and the ECART protocols are explained in this figure. In case of BB84 protocol, Alice chooses a one photon system that can exist in two-dimensional basis. Here we are working in the polarization basis. Now Alice and Bob decide to work in two mutually unbiased bases, HV or DA. DA means plus 45 minus 45. Alice randomly chooses between the two mutually unbiased bases and sends either a 0 or 1 to Bob. After receiving the photon, Bob then randomly chooses one of the two mutually unbiased bases and makes the measurement. If Alice and Bob were using ECART protocol, then they shared an entangled state given by psi equal to HH plus VB or equal to DD plus AA. Let me write HH plus VB or DD plus AA. In both cases, for the example shown in the figure, the shifted key is 0011. The original proposal by Bennett and Brassard was based on using two-dimensional variable, for example, polarization. But more recently, cryptography with higher dimensional variable is gaining increased attention, and BB84 protocol for two-dimensional variables has now been extended to higher dimension also. So I hope you understand. Let me explain this figure once more. Either Alice and Bob are measuring in VH basis or the DA basis. They both of them are mutually unbiased basis corresponding to each other. Now if Alice is now Alice choosing random bits which are 10010 whatever, and now in Bob's basis Bob are choosing Bob is also choosing Bob is also choosing his basis randomly, and now the beats are coming. Now if the now Alice's bases are given there, and Bob's bases are also given there. Now Alice's random bases are these, and Bob's random bases are these. Now whenever their bases will become same and the measurement of random bits will become same, then only they will get the shifted keys corresponding to HB 0, HB and 0. They have got 0, 0, 1, 1, and corresponding to this set of Bob's measurement, he has also got this shifted key, which is the 0011. In this context, we note that in OM states of photon span a countably infinite dimensional Hilbert space and are therefore a very suitable variable for higher dimensional quantum cryptography. One of the main advantages of high dimensional quantum cryptography is the increased value of maximum allowed transmission error, which for the two-dimensional case is about 17%. So this was the thing. Now if we solve one problem, then you will be able to understand how it actually works. So this is the problem to you. Now as I have described the BB84 or ECART protocol just now, so I wish that you have understood. If you not, then of course I will solve it, but give a look at this question and try to answer it, try to do it, and then I will solve it. So now let us solve this problem. This is very easy. I hope you guys have already done this, but let me do it. So it is very simple. The only instances when Alice and Bob will keep the measurement result are when the both happen to use the same basis, right? So we can directly write what it will be, what are the same bases. And in the instances, Alice and Bob will obtain the same measurement result since there is no eavesdropper or channel error. We are assuming that. So therefore the generated key and Alice and Bob will save at a variable that we can write from both bases directly as a Bob basis. Bob's random bits. So DA 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 HP HP DA DA HP HP DA DA HP DA HP HP DA DA HP DA HP 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 DA 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 HB HB HB. This is the basis that Bob has chosen. Now we will see the Alice's Bob. First one DA DA, so it will transfer 1. Second one is HB DA, so nothing. Third one is DA DA, so it will transfer. Fourth one is HB HB, it will transfer. Fifth one is HB HB, it will transfer. Next is HB DA, it will not. DA DA, it will again transfer. Then DA HB not, HB DA not, HB HB, it will transfer. DA HB, DA HB no, HB DA no, DA DA yes, HB DA no, HB HB 0 yes, 1 yes, DA HB no. So the finally shifted key, generated key will be 101011001. This is the answer. Okay, so now we will discuss about quantum teleportation. Very important. So the no cloning theorem prohibits generation of an exact copy of an arbitrary state of a particle. However, using quantum entanglement, it is possible to at least transfer an arbitrary state of a particle without actually transferring the particle itself. And this is known as quantum teleportation. And this is shown in this figure also, where it is showing that Alice is sending some phi state and PDC is coming, that is entangled photon, and it is only sending to a signal to Alice, not to Bob, but through the entanglement channel the phi state or information can be directly sent to the Bob without having any physical channel. And that's why although we are sending it to the Alice, it is automatically going to the Bob. That means there is some wire is happening, that means some teleportation is happening. And Alice and Bob share an entangled pair of photons that we need to mention, which are entangled in the polarization basis in this case. The two particles can be in any of the Bell state. Of course, it need to be Bell state. So maybe I can solve the thing step by step. But wait a minute. Okay. Alright. So phi plus minus AB equal to 1 by root 2 HA HB plus minus VA VB, or it can be any psi plus minus AB. These are the Bell states in polarization basis. Now let us assume that the entangled particles are in the following Bell state: psi minus AB, that means 1 by root 2 H A V B V A H B. Now suppose that Alice has another particle with an unknown state phi C that she wants to teleport to Bob. Alice does not know the quantum state of a particle, neither can she send the particle to Bob, but she still can be able to send the unknown state to Bob in the following way, which I will do now, which is called the quantum teleportation. Now let us write the state of Alice's particle, which is phi C, as alpha HC plus beta VC. That means alpha 1 0 plus beta 0 1, which means alpha beta, where alpha square plus beta square equal to 1. That means normalized. Now we note that the combined state of the two entangled particles and particle C can be written as a pure tensor product of psi minus AB and phi C. Okay, so we will do so. So that will become now psi ABC, that is psi minus AB phi C, equal to 1 by root 2 HAVB minus VAHB into alpha HC plus beta VC, which is equal to, I can just do the steps and follow the steps, and step by step I am doing everything, writing the steps, and next step it will become like this. Alice has two particles, particle A and particle C. Now, she performs a Bell state measurement on this particle. This simply means that she wants to see which Bell state her two particles are in. The Bell basis representing particle A and C, those can be written now in the same manner. I will just copy from here, but now it will be C. Now the above relations can be written in terms of, like, I can get HC in terms of phi plus minus and psi plus minus. I mean, all of these terms, these four terms we can get in terms of phi plus, phi minus, psi plus, psi minus in case of AC basis. So if we do so, then we will get HA HC equal to 1 by root 2 phi plus AC phi minus AC. VA HC 1 by root 2 psi plus AC minus psi minus AC. HA VC 1 by root 2 psi plus AC plus psi minus AC. And VA VC equal to 1 by root 2 phi plus AC minus phi minus AC. You can find it also, you just do it by do and check it that if it is coming or not, it will come this only. So now I can write this equation, this equation like this, what I am writing now, which is VB minus alpha by 2 psi plus AC psi minus AC HB plus beta by 2 psi plus AC psi minus AC VB minus beta by 2 phi plus AC minus phi minus AC HB. Okay. Now this above equation can be rewritten as one by 2 phi plus AC alpha VB minus beta HB plus 1 by 2 phi minus alpha VB beta HB plus half psi plus AC minus alpha HB plus beta VB plus half psi minus AC alpha HB plus beta VB. So we find that particle A and particle C are equally likely to be found in any of these four Bell states, and the probability is 1 by 4. As we can see, 1 by 2 are there in here with the in multiplication with each of the states. So 1 by 4 is the probability. So after Alice has done the Bell state analysis, she sends that information to Bob, and based on that information, Bob decides an unitary transformation, which guarantees that he has the original state. And here how it is done. 1. Suppose Alice's measurement gives her Bell state phi plus AC. The state of Bob's qubit will be alpha VB minus beta HB. So Bob makes the unitary transformation given by U phi plus, that is 0 1 minus 1 0, such that the state of Bob's qubit becomes this. Let me write, it will be much more clear. So Bob's makes the unitary transformation 1 0 minus 1, sorry, 0 1 minus 1. With the experience, if you calculate this much many a times, then you will be able to understand that what will be the unitary transformation even. Then Bob's qubit becomes and this is nothing but the phi state which Alice wanted to send. Now suppose Alice's Bell state is phi minus AC. So Bob's qubit will be, so Bob makes the unitary transformation such that it becomes now again Alice's measurement gives her the Bell state, suppose psi plus AC. Then Bob's qubit will be minus alpha plus beta. So Bob's make an unitary transform now. Which is minus 1 0 0 1. So if you do that, then it will again become now if number 4, Alice's measurement gives her the Bell state psi AC. The state of Bob's qubit will be VB. So Bob makes the unitary transformation given by and it will become thus we see that Bob gets the same state psi that Alice intended to teleport. The quantum teleportation protocol that we have outlined is for a qubit here, that is for a photon in a two-dimensional Hilbert space, but in general one can have quantum teleportation in n-dimensional Hilbert space also. So this is the quantum teleportation protocol. Now based on this, there is a problem given that suppose Alice and Bob share two entangled particles in state psi minus AB, this. Now suppose that Alice has another particle with an unknown state phi c with alpha square plus beta square equal to 1 that she wants to teleport to Bob. Describe mathematically the teleportation protocol in detail. This is nothing but what I have just solved. This is the question and this will be the answer which I have just solved. So now you try to understand how this has happened and if you can do it by yourself, and try to do it by yourself now. So this is the problem 3. So after this we will solve some more problems, but let take some rest and you try to understand this problem whatever I have just done very carefully. Okay, I'll come back again and we'll start discussing about these problems, this problem 4, problem 5, and we'll end up the course. So you guys are now aware about quantum cryptography as well as quantum teleportation. So please give it a give it a look. Give it a look. Give it a look. So okay. Okay, please go through this problem. We will now solve this problem 4. I was just preparing the 2 photon path diagram for this. That's why it took time. So please go through this problem. I will solve this. So it is saying, consider the following 2 photon interferometer with the 2 photons produced by parametric down conversion. Using a pump of wavelength lambda 0, we represent the coincidence time window t by t coincidence and the coherence length of the pump field by L coherence P, and the coherence length of the signal idler field is L coherence. So what is the question is that it is asking, draw the 2 photon path diagram of all the alternatives that lead to the coincident detection at detectors dA and dB. This is the first part. That is why that is what I was doing just right now. Then the second part, it is saying, suppose that the coincidence time window is less than y minus x by c. Y, x are given to you in this figure, where c is the speed of light. Also assume that y minus x less than L coherence and y minus x less than LP coherence. Calculate the coincidence count rate of the detectors dA and dB in terms of x, y and lambda 0. So for the first part, draw the 2 photon path diagrams of all the alternatives at detectors D and dB. This is the answer. The answer is in slide. So these are the cases that it can happen. How I have a lot of time I have gone through this 2 photon path diagram, that how we should plot it and how to what are the states or how to do it. So by this time I hope you guys all are aware about that. So we need to check that through which direction signal and idler comes, all the possibilities we need to draw, and all the possibilities are that they both can come. The one is both can simultaneously go through this path in this Michelson, and both can simultaneously go through this path directly. I mean, one is this path, one is this path, one is going through this path while another is going to another path, and vice versa. So based on all of these are the 2 photon path diagram, and corresponding to that you need to calculate the phi, that is the phases, and and of course you need to calculate del L and del S. But first question is that draw the 2 photon path diagrams for all of the alternatives that lead to the coincident detection at detector D and dB, that is given over there. Now suppose that the coincidence time window is this. Also assume this. Calculate the coincidence count rate of the detectors D and dB in terms of x, y and lambda 0. Let us solve this part now. Then we go to the question. Yes. Now let us solve the part B. So when t coincidence is less than y minus x by c, the third and the fourth alternatives do not contribute anything to the coincidence. What are the third and fourth? These are the third and fourth coincidences. So when this case happens, then 3 and 4 do not contribute anything to the coincident detection. So only the alternatives 1 and 2 will cause the coincidence. Thus we need to compare between 1 and 2, and we will get the del L and del L dash and del phi. Therefore the coincidence count in this case will be RSI. We have lot of time calculated this. I am not explaining or giving the formula again, rather you can directly put the things here. K into 1 plus cos 2 pi by lambda 0 2y minus 2x and this. Okay. So in this case, all the four in this case, among all the four alternatives, only two will participate, and RSI will be this. And as delta L is equal to 0, it is almost gone, and delta L is 2y minus y 2x. And finally, we will get this. And now the question part 3, it is asking, now suppose that a coincidence time window T coincidence greater than y minus x by c, where c is the speed of light. Also assume that this is greater than coherence, L length of coherence, and less than pump coherence length. Calculate the coincidence count rate of detectors T and dB in terms of x, y and lambda 0. In this case, all the four alternatives will contribute to coincident detection. However, y minus x greater than L coherence alternative for this case, for this reason, alternatives 3 and 4 will not interfere with any other alternatives. Hence it will only cause a constant background. Since all of the four alternatives are equally probable, the coincidence is given as this one. Okay, so this is the case. This is the D answer. Okay, now let do this problem 5. This will please you go through this problem, and I'll give you 2 minutes, then I will solve it. Okay, so let me start solving this problem. Whatever the question is, you have already gone through, I hope, but let me speak once. First, it is psi xi is given for two photon wave function position basis as well as in momentum basis. Now it is saying calculate the conditional uncertainty in the position and in the position of the signal photon. Calculate the conditional uncertainty in the momentum of the signal photon. Find out the condition in terms of W and sigma such that the above two photon wave function violates the conditional Heisenberg uncertainty relation. Fine, let me do so. So psi xi is given to you. So the two photon problem 5. So two photon position probability function will be P xs xi, that is equal to psi xs xi square, which is equal to a square exponential minus of xs plus xi square by 2w square and exponential minus of xs minus xi square by 2 sigma square. This. Okay, I have just squared the psi xs xi. So now we will get the conditional probability if we do xs and make xi equal to 0. that will make, or that will give exponential minus x square by 2 1 by w square plus 1 by sigma square. The standard deviation of the function is called the conditional uncertainty, and if you find it, the standard deviation, then it will be plus w square plus 1 by sigma square. Now part B, it is saying calculate the conditional uncertainty in the momentum of the signal photon. Momentum basis. Psi ps pi is given. I will just calculate the probability. Two photon position probability function, momentum probability function is ps pi equal to psi ps pi square equal to a the square exponential minus ps plus pi square omega square by 2h bar square into exponential minus ps minus pi square sigma square 2h bar square. Okay. So we get the conditional momentum probability of the signal photon by substituting pi equal to 0 in this equation, and thus it will become a dash square exponential minus ps square by 2 w square by h bar square plus sigma square by h bar square. The standard deviation of this function is will give the conditional uncertainty w square by h bar square plus sigma square by h bar square in the momentum basis. So this is the part B, and now the part C, it is saying find out the condition in terms of w and sigma such that the above two photon wave function violates the conditional Heisenberg uncertainty relation. Okay, it's very simple. We'll just do this, and now it is saying violate, that means less than h bar by 2, and now I will put the relations what we got for delta x is conditional and delta p is conditional. Now it will become omega sigma, I mean w sigma I am doing nothing but the simple algebra. So this condition is valid. So the above condition, like the Heisenberg uncertainty principle will be violated only if omega equal to sigma. Otherwise, it will not. Otherwise the Heisenberg uncertainty condition relation will be fulfilled. Therefore, for the two photon function, the conditional Heisenberg uncertainty relation is always violated except when omega equal to sigma. Do you understand the last statement? The last statement is the above two photon wave function, the conditional Heisenberg uncertainty relation is always violated when except when omega equal to sigma. So the answer is so. This is the thing, and this was my last question for today. So just give a look at it once again what I have done, then I will formally end this today's class. Okay, so I think you guys have understood all of these problems, what I wanted to convey, and what are the problems we did for the last time today in this week 12 course, week 12 class. So this was our last time we are meeting for this problem solving and doubt clearing session on every Saturday. This is from the this is a bit attachment with the course that I feel every time whenever I end with a course that now no more I will be able to discuss about this course for this semester with you guys, but of course always you get in touch with the through the through any of the platforms that I have told several times for you. And I hope please go through these videos which you have already publicly available in the video in my YouTube channel. You will get to see all of them, and for any necessary anything that you need, you can always contact with me for discussion. And yes, so this is these are the videos, all of the videos are available, and this is the Google Drive folder where you can access all of the lecture, all of the classes, discussion sessions, problem solving, like whatever I have done, all of the write-ups, as well as the these questions which are there in these slides, that you can access the slides also. These are the slides. And of course this is a syllabus, and I will formally complete this class in next 1 hour summary session, and there we will formally go through the syllabus ones and all of the week's contents, and for the last time we will meet for that. But I think today we have done all of the things that were left for today. So first I will just go through for today's things. So we have done several problems. We have learned about quantum cryptography, BB84 Ricard protocol. So we solved problems again. We learned about quantum teleportation, and we solved problem again, and there were several problems we solved again and again for related to the two photon wave function. So this was our today's plan and today's discussion session, and I hope you guys have enjoyed and all of the information you already have. So I say now goodbye to everyone formally for this week 12 and this is the last formal class on this Saturday 5 to 7 p.m. For week 12 for this Coherence and Quantum Entanglement course by through SWAM portal by NPTEL. I hope you guys have enjoyed. So see you for the 1 hour summary class. That will be the last time we will meet, and for this it's a final goodbye for this week 12 with this course. I hope you guys have enjoyed. Bye.